In mid-2025, India reached a milestone. Half of its total installed electricity capacity now comes from non-fossil sources. This threshold shifted the national systemic risk. The primary bottleneck is no longer raw energy generation, but the physical transmission and distribution of that power. Solving this spatial constraint requires 137,500 circuit kilometers of new high-voltage transmission lines by the middle of the next decade, according to mandates from the Central Electricity Authority. This expansion is designed to integrate 900 gigawatts of non-fossil capacity into the macrogrid, requiring an architectural overhaul that will cost trillions of rupees. However, this domestic build-out is colliding with global economic volatility, driven by geopolitical instability in the Strait of Hormuz. Because the Indian economy imported over 88% of its crude oil requirements in fiscal year 2025, disruptions in the strait pushed Brent crude prices past $105 per barrel, weakening the rupee. To defend the currency, the Reserve Bank of India implemented defensive policy rate hikes. For grid operators, higher interest rates directly inflate the weighted average cost of capital, making it more expensive to finance massive infrastructure projects. These capital pressures, combined with the sheer volume of material needed for the grid, are forcing the domestic wire and cable industry to change its operational model. Manufacturers are moving away from the high-volume production of low-margin construction supplies to focus instead on high-technology, capital-intensive cable systems. The success of this transition depends on a single factor. The physical conductive cable is now the primary link ensuring India's macroeconomic stability and energy security. The flow of energy begins with a geographic mismatch. India's highest solar and wind yields are concentrated in western and southern states, while the peak load centers are located in the industrial corridors of the north and east. Bridging this distance requires a massive expansion of extra high voltage and high voltage direct current infrastructure to move bulk power across state lines. At the generation node, the scale of material required for a single utility-scale solar park is immense. A standard 1 megawatt solar photovoltaic installation requires approximately 50 kilometers of specialized DC cabling to connect panels to inverters and transformers. These cables must survive decades in harsh environments, characterized by constant ultraviolet radiation, extreme thermal fluctuations, and mechanical stress. To reduce resistive power losses and lower overall balance of system costs, the industry has adopted 1500-volt DC architectures as the national standard for large-scale parks. Protecting the core at these high voltages requires advanced material science. Manufacturers use specialized electron beam cross-linked polyolefin insulation to prevent the dielectric degradation that causes short circuits. These engineering specifications are strictly enforced by the government through the legally binding BIS IS 17293-2020 quality standard. This combination of extreme environmental stress and unyielding safety mandates removes unorganized, low-quality suppliers from the utility-scale node of the grid. While generation nodes are located in remote deserts, the terminal edge of the grid exists within the hyperdense, often inefficient urban distribution networks. To modernize these local networks, the government launched the Revamped Distribution Sector Scheme, a multi-trillion rupee project aimed at state-owned discoms. A primary objective of the scheme is to lower aggregate technical and commercial, or AT&C, losses to a range of 12 to 15% by 2028. To stop power theft and reduce technical line dissipation, utilities are replacing bare overhead conductors with insulated aerial bunched cables and underground low-voltage lines. This physical upgrade is paired with a digital mandate, the rollout of 250 million prepaid smart meters across the country. However, most state discoms carry too much debt to fund the massive capital expenditure required for this advanced metering infrastructure. To bypass this debt, the rollout uses a TOTEX, or total expenditure, financial model, where a private agency designs, funds, and operates the infrastructure. This model transfers the capital burden away from the utility, accelerating the modernization of local grid control architectures. The result is an exponential increase in demand for multi-core control cables and fiber optics, which are needed to connect smart meters to supervisory control and data acquisition systems. By integrating these physical and digital layers, the local distribution network becomes a bidirectional, data-rich architecture capable of managing volatile urban demand. At the ultimate edge of the grid are high-margin, high-density terminal nodes, hyperscale data centers, and electric vehicle networks. India's data center market is projected to reach $27.2 billion by 2032, driven by forced data localization and the growth of AI workloads. AI architectures require ultra-low latency server-to-server communication, which is pushing standard optical fiber to its physical capacity limits. This has led to the adoption of multi-core fiber, or MCF, which places multiple data cores inside a single optical strand to maximize bandwidth in limited duct space. If data centers require high-density connectivity, the electric vehicle network requires high-density power. India needs approximately 2 million new charging stations by 2030 to support the influx of EVs. Charging heavy commercial EVs at megawatt speeds, ranging from 500 to 900 kilowatts, generates immense thermal loads within the charging cable. The standard copper cable, thick enough to carry that amperage without overheating, would be too heavy and rigid for a human to manipulate. To solve this weight constraint, manufacturers integrate active liquid cooling directly into the charging cable, allowing for a smaller copper conductor that can still handle extreme amperage. At these high-density nodes, the role of the cable manufacturer is defined by its ability to solve for multi-terabit data physics and extreme thermodynamic constraints. Looking at the grid in aggregate, the volume of physical conductive material required for this transition is measured in billions of dollars. However, this massive national demand is now colliding with a volatile global supply of raw materials. This chart highlights a structural deficit in the global copper market, caused by declining ore grades and a lack of new mining capacity. Financial models forecasting LME copper prices at $13,000 per ton create severe margin compression risks. To mitigate this volatility, top-tier manufacturers execute upstream backward integration, building in-house production for copper wire rods and polymer compounds to secure supply chains. In addition to these supply-side shifts, the government has introduced a powerful defensive moat, the expansion of Bureau of Indian Standards mandates. Strict quality control orders now cover raw materials and specialized cables, creating a non-tariff barrier that prevents the use of substandard imported goods. The capital required for backward integration, R&D, and continuous BIS compliance is systematically removing small regional players from the market. This consolidation is accelerating, with organized Tier 1 manufacturers projected to capture 88% of the market share by 2032. Major renewable energy and data center developers must now secure manufacturing capacity years in advance through long-term inflation-indexed offtake agreements. Technical complexity, global metal scarcity, and regulatory mandates have consolidated the market, making specialized manufacturers the critical providers for India's future power and data infrastructure.